Right, so today we're going to continue talking about cosmology, and we're going to be talking about the origin, start of the universe, and the conditions in the early universe. And we had to skip a couple of slides last time, so let's go back. So we talked yesterday about this discovery that all galaxies are moving away from one another, and that not only are all galaxies moving away from one another, but the galaxies that are furthest away from us are moving away at the fastest speeds. And this was Hubble's law. That's the first equation in red there. V is a constant times r, where V is the speed at which the galaxy is moving away, and r is its distance from us. So we find that this obeys an approximately straight line, and in next week's lab you'll take some kind of observations via computer simulation and look to show this. So by kind of tracing back, by trying to follow this back, if we just assume that the galaxies have all been moving at these speeds, then we can figure out the time it would take to kind of follow them all back in time to a single point. And that allows us to estimate the age of the universe, which comes out to be something like 14 or 15 billion years. Now, if we only had that one kind of piece of evidence, that would be pretty sketchy. In terms of evidence that there is a Big Bang origin for the universe, we've got similar estimates of the age of different things, both on Earth and out in the cosmos, which tend to sort of agree with this estimate. There are also other different pieces of evidence for the Big Bang theory, and one of them comes from what's called the cosmic microwave background radiation. So to kind of understand what that means, we need to just grab this formula kind of out of thin air, but it comes from like thermal physics. I mean, basically all hot bodies radiate, and if you assume that you have a so-called black body, which is just this particular kind of profile of radiation, then it has this kind of spectrum which has a peak, which has a maximum in the radiation at a wavelength which is related to the temperature by the reasonably simple formula in the red box. So this observation by Penzias and Wilson, they originally thought there was like bird crap on their telescope, because wherever they looked there was just this like fuzz, but it turned out that when we now look at this more closely, we see that the entirety of, Earth is bathed in this radiation, and it doesn't matter what direction you look, there's this radiation coming towards us. And it corresponds to a black body spectrum with a temperature of about 2.7 Kelvin. And it's kind of an amazing, one of these things where, usually experimental results and theory, there's a little bit of discrepancy between them. When you plot the experimental results on top of the theoretical estimate, it's kind of an amazingly good fit to this black body spectrum. So this had already been theorized that if there was a Big Bang at the start of the universe, then in the very early universe things were really, really hot, and we should still be able to see the radiation from that really hot universe, because it takes some time to make its way all the way to us. Because of the stretching of space, then it ends up with this kind of longer wavelength. But this temperature and this kind of wavelength of radiation that we see is actually like consistent with this Big Bang theory. So that's another one of the pieces of evidence. There are now these detailed maps of this cosmic microwave background. It's actually amazingly uniform. It's almost the same regardless of what direction we look. So although that color map there is showing us different points in the sky, the cosmic microwave background has very slightly different. Actually, don't know whether that's wavelength or intensity. Looks like it's intensity. But in either of these properties, you see that it's almost uniform, and it's actually only 1 part in 100,000 that these variations are, so tiny amounts. So this is one of our other pieces of evidence that supports the Big Bang origin of the universe. So we have this kind of picture that the universe started with a Big Bang. It's our current best theory. There was a period of so-called inflation, and then we'll talk in a second about maybe what happens in the early stages. At some point about 300,000 years later, radiation starts to be able to propagate, and this light from the very early universe. If we look far enough away, we're able to see that light from the very early universe. This is just another schematic which is supposed to be, again, showing us this kind of our picture of how we think things evolved. We'll come back to this a little bit later, possibly in tomorrow's lecture. Okay, so then shortly after the Big Bang, we think that physics was quite interesting and quite different because everything was kind of crammed into a relatively small space and was super, super hot. And since then, it's been expanding and cooling. So we have this kind of picture of the different kind of stages through which the universe evolved to get to the stage where we're at now, where the universe, we think, is matter-dominated, and we have stars and galaxies. And you'll see that gradually the temperature is going down as we move from left to right. Time is along the top, and it's a logarithmic scale, so that by the time you get halfway along here, you're still only at 10 to the minus 4 seconds after the Big Bang. So if we flip this on its side, then we can get a little bit of more detail here. And what you'll notice inside the kind of colored triangle is some words that we mentioned last week when we were talking about particle physics. And this is really where particle physics and cosmology kind of come together, and this is why it makes sense to talk about these very, very tiny things and like the universe as a whole at the same time. So you might remember in Thursday's lecture we had this picture that's up in the top left-hand corner where we were talking about grand unified theories and theories of everything. And this is this kind of holy grail of particle physics to unify the forces. Why are there 4 fundamental forces that we can observe? What we think is that they are all possibly just aspects of like one single kind of unifying force, and that we only observe them to be different because we're now looking at things where the energies are quite low, at least compared to what we had in the very early universe. So we think that within the first, 10 to the minus 43 of a second, that's a fairly short amount of time, temperature was like 10 to the 32 Kelvin, and all of the forces were equivalent to one another. Now then the picture goes that gradually these forces kind of separate from one another as the energy gets lower. So first of all, gravity becomes a separate force that isn't any longer equivalent to the other ones. Then about 10 to the minus 6 of a second, the strong force becomes a separate force. We now have the quarks able to combine with one another to form hadrons. And gradually, things kind of cool, and the soup, the primordial soup thins out. So before about 10 to the minus 4 of a second, the photons that were in the universe were so energetic that they just spontaneously created particle-antiparticle pairs all over the place. And so they didn't really propagate too much. As we go gradually lower down in this thing, as time progresses on, we get to eventually into the kind of palish green area at the bottom where we can form nuclei. Before that, the energies were too high, the nuclei just flew apart. But still, as we go further down here, even down to like 1,000 seconds, there's way more energy in the radiation than in the matter. And so we're just kind of constantly creating and annihilating particles, and the whole thing is a gigantic mess. And one of the important things that happens from the point of view of like our observations and our understanding is that when we get down to the bottom section, I didn't have space for the text on that slide. When we get down to that bottom section, that pale blue section, when you get to about 300,000 years after the Big Bang, the temperature, we think, was down to about 3,000 Kelvin, and finally we were able to form atoms. So there were nuclei before that, but the energy was too high for the nuclei to be able to capture the electrons. The electrons had too much energy and they just fly out. But after about 300,000 years, we could form atoms. So now that the nuclei are able to capture the electrons, the photons can actually propagate. Previously, if photons were trying to propagate, photons that are of course part of the electromagnetic spectrum, like light, if photons were trying to propagate, they would just get scattered off of all the free electrons that were flying around. So about 300,000 years, the nuclei are able to capture those electrons, and light is able to propagate. Now, maybe I'll skip on from there. One, this is important because what it means is that we actually can't see any further back in time than about 300,000 years if we're using electromagnetic radiation. So we said that was electromagnetic radiation, light, microwaves, radio, all that stuff. That's our kind of only, or maybe not quite only, but mostly that is how we observe the universe. And prior to about 300,000 years, light wasn't able to propagate through the universe, and so we can't see anything from earlier than that. So now you may have heard about detections. Recently, this was, the team got the Nobel Prize for first detections of gravitational waves. So one of the exciting things about gravitational waves, and we'll talk a little bit about gravitational waves today, is that they offer, like it's an alternative wave, it's an alternative thing that might be propagating through the universe. And in principle, there's no reason why the gravitational waves from earlier than that 300,000 years couldn't propagate through, and if they're still propagating through the universe, which they should be unless they've been absorbed, but some of them should still be there, the gravitational waves offer us the possible opportunity to look further back in time than what we've been able to do so far. Right, we're going to get the Kahoot rolling with an early question. Players. All right. So we cannot detect photons emitted earlier than about 380,000 years after the Big Bang. So why did we say that was? Either there are no atoms before that time, the universe is opaque. There are no atoms, so no atomic energy level transitions. No photons before that time, or the photons are redshifted to wavelengths we can't detect. Okay, a pretty even split. So there were photons, but there were so many free electrons that the universe was opaque. The photons weren't able to propagate through. Because there weren't atoms, there were just nuclei. The nuclei hadn't managed to gather up the electrons yet, so there were too many electrons in the way. All right, come back to some more questions as we go through. So, one of the exciting things about gravitational waves, I mean, the prospect is to help us better understand the gravitational force, and we'd like, that's going to help us to figure out, well, how might that be related to the other forces? But the other thing is that the hope is that it may be possible to kind of see further back into the origins of the universe. Now, in order to talk about gravitational waves, we need to, and about gravity and about the kind of overall properties of the universe and where it might be going, we have to kind of dip a little bit into an area called general relativity. So Einstein came up with this theory of general relativity, and the kind of principle, one of the principal statements of that is the so-called equivalence principle. And the equivalence principle says that no experiment can be performed that can distinguish, or where you can tell the difference, between a uniform gravitational field and an equivalent uniform acceleration. So this is telling us that gravity is like the equivalent to some kind of accelerating frame of reference. Now, as an example, if we have a person standing in a lift and they are holding a book and they let go of the book and the book falls to the floor, there are two ways that could happen. Either the book falls under gravity, which is probably what you'd expect if you were like standing in a lift and you let go of a book, because we know that here we're in a gravitational field, obviously. But the other option is that the lift is out in space where there's no gravitational field, but is accelerating at an acceleration that's equal to g, the gravitational acceleration on Earth. And the book would fall in exactly the same way, and there's no way to tell the difference between the book falling under gravity or the book dropping because the lift is accelerating. So this is one example of an experiment where you drop a book and you look at what it does. But this equivalence principle states that there's no way to distinguish between being in a gravitational field and being in an accelerating frame of reference. So why this is interesting for us at the moment is because we're going to be thinking about how light propagates in the universe. And if we think about, we know that light is made of little photons, of little particles, and that in principle they should do the same as what the book does. So now we imagine that our lift has a hole in the side and there's a beam of light coming through that hole. Now, if you're in an accelerating frame of reference, then the lift should move up and the photons should appear to fall down in the same way as the book does, which means that the beam of light should curve as it goes across from one side of the lift to the other. But the equivalence principle says that we cannot tell the difference between that experiment and the situation where the lift is not moving, but but it's in a gravitational field. And so that tells us that gravity has to bend the path of light. We've got another Kahoot question. What does the equivalence principle say? Gravity is the same thing as the curvature of space-time. Effective gravity is exactly equivalent to the effective acceleration. We can't distinguish between motion at a constant speed and weight. All observers will always measure the same weights for moving objects. Yes, so the effect of gravity is exactly equivalent to the effect of acceleration. All right. So, gravity bends the path of rays of light. So now we've got this kind of cartoon where we can imagine what happens when we've got a telescope that is looking at some kind of blob of matter. Maybe it's a galaxy cluster or something, this red blob of matter in the middle. And directly on the other side of that is a galaxy. Now, we can still see, it turns out we can still see this galaxy so long as the parameters are right. We can still see this galaxy behind because the light rays that are emitted by that galaxy will be bent by the cluster in the middle. Turns out that they're bent kind of towards where the mass is. So the gravitational field of this blob of stuff will bend the path of the ray of light, and it can be bent around so that we can still see that galaxy from using our telescope, because we can still collect the rays of light that come from it. Now, obviously, the mass, the gravitational field of the red blob in the middle has to be right to bend it just the right amount. It doesn't always work. But what we think we would see then, if we imagine this picture, and we're just drawing it two-dimensional because that's easier. If you're this telescope, if you're looking at the pictures from this telescope, you would see that galaxy by looking along this white line, right? And if you kind of follow that in the direction that the white line goes, then where you think the galaxy is actually up here. But if the light rays are being bent kind of down underneath as well, you might also see an image of the galaxy down at the bottom. Now, this is a kind of idealized picture where everything looks nice and symmetrical, but what we would see is these kind of distorted images. Now, this process is called gravitational lensing, and it's called gravitational lensing because that red blob, that cluster of stuff in the middle, is acting like a lens, right? It's focusing the light rays into the telescope. Now, come on. So then, this is a good way to kind of see galaxies that are behind other stuff. But actually, it's not principally used for that. It's principally used to understand the properties of the red blob in the middle, which here is supposed to be a galaxy cluster or something. Because by looking at how much the light rays are bent and how distorted the image of the background galaxy is, that can give us clues about what the gravitational field has to be in the red blob that's doing the actual bending of the light. So the amount that the path of the light rays bend is proportional to the gravity. So this allows us to basically take a measurement of the mass and how the mass is distributed in this red blob in the middle by looking at how it bends light. So this is one of the principal techniques that's used for studying what's called dark matter. We'll talk about that a bit more a little bit later. So there are some examples here of gravitational lensing at work. This is, let's see, if we go back to this cartoon picture, if you kind of imagine this now in 3D, if the distribution of mass in the red blob in the center of the picture is sufficiently symmetric, if you imagine this in 3D, you would just kind of rotate the whole thing around and you should see a whole series of galaxies in a ring, because there's nothing special about this 2D plane. So this is an example, or thought to be an example, of this at work. The bright blob in the middle is the object that's doing the lensing. That's our lens. And then this kind of fairly symmetrical ring around the outside is like a whole kind of blurred series of images of that object that's hiding behind it. So it's more common that your lens is not completely symmetrical and therefore it doesn't bend the light into your telescope from all directions, and that instead you get 2 or maybe more images of that galaxy that's hiding behind. So here are a couple of examples. They're not super clear on the screen, I would have to say. But again, the object in the center is our lens. And then here we've got 1, 2, 3, 4 lensed images of the object hiding behind. And here's another example here of probably 1, 2, 3, 4 images that are being created by, again, it's the reddish blob in the middle. Now, I don't know whether you guys have seen these James Webb Space Telescope images. They've released 4. They released them a couple of weeks ago. The first images from JWST, and some of the kind of initial commentary on it was, oh, it's rubbish, it's all blurry. Now, the blurring that you see in a lot of these, the reason that some things appear to be smeared out is associated with this kind of warping and lensing of the light. There are kind of thought to be a whole bunch of lensed images of lensed galaxies, because this is looking kind of directly at a galaxy cluster. I can't remember which ones they are, but you know, you can look at the actual spectra of the light from all of these things and kind of determine that they're actually the same object, or at least, you know, they have exactly the same characteristics and are likely to be the same object. So there are a whole bunch of kind of 2, 3, 4 images of like the same little galaxy in here. So there's going to be lots more coming on this in the next few years. And this is then kind of revealing the properties of the matter in that globular cluster that we're looking directly at. Got another question. True or false? During gravitational lensing, light curves around the lens object so that its rays can hit us. True, yes. Right. So now we're going to kind of take another step into the, weirder world of general relativity. So if you accept that light will be bent in the presence of a gravitational field, so now we have to go to another one of the kind of fundamental principles, which is probably one that you have heard, that nothing can move faster than the speed of light, that the speed of light is an absolute maximum. So this means that light has to travel along the shortest path between any 2 points. Otherwise, you could have some signal, some object that arrived faster by moving along a shorter path. And if it could arrive earlier by kind of somehow traveling along a shorter path than light, then it would have moved faster than light, and that's not possible. So what this tells us is that light must be traveling along the shortest path between any 2 points. But if light is traveling along a curved path, then that means that the space itself has to be curved. Because if the space was flat and light traveled along a curved path, there would be a shorter path between the points, right? So this tells us that the mass that generates gravitational fields and can bend light actually curves space-time itself. And this is like almost impossible to visualize in your head in three-dimensional space that we live in. If you think about the universe being 2D, it's a little bit easier because then you can have a third dimension for your brain to imagine this curvature in. And so usually the kind of picture that we have is that space is like a rubber sheet or a trampoline or something. When you put a heavy object on it, it bends the space around it. And then if you were to roll a marble or something like that along that rubber sheet, it would travel along a path that curved on that curved space. So that's what's supposed to be shown here by the green lines, is this kind of rubber sheet that's representing our 2D universe in that picture. Now, obviously, the universe is 3D, and so that curvature has to be happening in some kind of fourth dimension. Hard to visualize 4D space in your head. Maybe some of you can, but most people cannot. Right, so we want to talk about gravitational waves, which are eventually kind of disturbances into space-time that are caused by particularly violent events. And the experiments that are now being done to try to detect gravitational waves are using a technique that's extremely similar to this very old kind of classical experiment from the 19th century. So back in the 19th century, it was thought that light moved in some kind of medium. It was called the ether. So this has since been disproved, right? Principally, or in large part by this experiment. But it was assumed that light moved in some kind of medium. And then it was known that the Earth orbited the sun back at those times. And then it was assumed that either the ether, if the ether is some kind of medium and the Earth is in that medium, then either it's stationary or the ether is being dragged along by the Earth. So there was this suggestion that there should be a relative motion of the Earth and the ether, and therefore that if light travels in this ether wind, then we should be able to detect a difference in the speed of light depending on which direction we're moving with respect to the wind, right? If we're moving in the same direction as the wind, we should measure a relatively slower speed of light, whereas if we were to move in the opposite direction to the wind, it should appear that light traveled faster. So Michelson and Morley set up this experiment to try to detect this difference in the speed of light in different directions. Now, it's probably the most famous kind of failed experiment in history, but the fact that it failed, or it didn't fail, but it showed a null result. It showed that there was no difference in the speed of light, led to the development of special relativity and whole branches of physics. So the way that it was supposed to work was you have a light source and it shines on the object in the middle as a kind of half mirrored sheet. It's half mirrored so that sort of half of the beam of light will travel through it and will reflect off the mirror on the other side. The other half will be reflected off it and will hit the mirror at the back there. Those will reflect the two beams. They should come back again partially, either reflect or pass through, and some of each of those signals will be detected in this telescope. Now, if the speed of light is exactly the same in both directions, then you shouldn't get interference fringes, but the way that it was set up was that if there was some difference in the speed of light, then you should get this kind of interference pattern that was predicted. Now, this is showing you can barely even see the data. The data just looks flat if you plot the theoretical prediction in full. This is the theoretical prediction multiplied by a factor of 1/8, and it's still enormously more than what was actually observed. So that was 19th century. That was, going back to looking at the propagation of light waves. So now the same principle is being used to search for gravity waves. So general relativity predicts that if we've got masses that are sufficiently large, they should be able to create waves in the space-time continuum. Think about those as being like waves that are propagating on that rubber sheet that we talked about that represents the curved space. So there's been a whole series of experiments that have tried to detect this, and finally there were observations of gravitational waves that were made by this detector called LIGO. So it uses exactly the same principle as that Michelson-Morley. It's an interferometer. LIGO stands for Laser Interferometer Gravitational Wave Observatory. The principle is the same. You shine out a laser, it hits a half mirror, and will propagate along these two long arms. The signal is then reflected back and collected. And the idea is if there is a gravitational wave, that should cause a distortion in space-time and should make one of those paths that the light travels a very, very slightly different length than the other one. So they're set up to be exactly the same length, and like the precision is ridiculous that they have to get to. But if there's a gravitational wave, the idea is that distorts space-time, it slightly changes the length of one of those arms, and the signals will come back no longer exactly out of phase. Now, this is more Nobel Prize winning stuff. So these are the first detections of gravitational waves. They come from, usually you need some gigantically massive objects doing something super energetic to create gravitational waves that are sufficiently strong for us to detect. And this first observation comes from the merger of two black holes. So black holes, obviously enormously massive objects, and they can merge with one another. They can spiral towards one another. When they merge, it creates an enormous, or relatively enormous, disturbance in space-time. So what we're looking at in some of these plots are the data from the papers where they match the theory and the observations. And of course, it's all about beating down the statistics and the uncertainties in order to kind of confirm a measurement. Right, since then there have been a number of other observations, again with LIGO, of these gravitational waves, and more of these LIGO type observatories are planned, some out in space, to try to detect more of these gravitational wave signatures. This is supposed to be showing us kind of roughly the way in which two massive objects that are spiraling around one another would cause disturbances in space-time. And these ripples should be basically tiny, tiny expansions and contractions of space that we hope to measure. All right, we've got our last Kahoot question. LIGO is a state-of-the-art experiment for detecting gravitational waves. How does it work? That's a bit small. Sorry, couldn't make that any bigger. So either A, small changes of the gravity field cause gravity waves that affect the photons. B, photons are collected which allow the detection of black hole mergers. C, two laser beams, initially out of phase, reflect off mirrors. The space between the mirrors is stretched and squashed by the passage of gravitational waves, creating an interference pattern. Or D, interference of light waves and gravity waves causes a distinctive pattern of fringes. Yes, so the right answer was C, it's the stretching and squashing of space-time that's changing the paths that the laser has to travel that we're trying to detect. All right, what does our podium look like? All right, good work to those people. So, I think that's us done. So we will be talking tomorrow. Tomorrow we're going to wrap up our discussion. We're going to be talking about the shape of the universe and what that tells us about the fate of the universe. We're going to be talking about dark matter and dark energy and other exciting and weird and wonderful stuff. So I'll see you then.